Hello everyone, welcome back to LeetCode Daily Live where I do the daily question, raw and cut. So we actually have a hard today. I think it is similar to yesterday's one in terms of the concept, but yeah, so this one is called count good triplets in an array. So yeah, that's why I think it is kind of similar to yesterday's, but let's see, maybe it is an entirely different question. Uh, so what are we given? So we're given a two nums array uh, of length n, and both of them are permutations of 0 to n minus 1. So that just means like all of them contain like these elements, but like they're mixed up. So a good triplet is a set of three distinct values which are present in increasing order by position both in nums1 and nums2. So in other words, if we consider position 1 phi as the index of the value phi in nums1, and then pos 2 phi for value phi in nums2, then okay, yeah. So if you pick x, y, z, and then so if you pick x, y, z, and then like nums1 x is smaller than nums1 y, which is smaller than nums1 z, and the same thing happens for for well for the second array, it would be a good triplet, and we want to return the total number of good triplets. Yeah, so I did see the bound when I first like looked down here. So yeah, they're quite long. So and we are finding triplet as well. So that means um we have to somehow find a n, like a on or n log n solution. So yeah, but the other thing which is interesting is that it is a permutation instead of just like completely random numbers. So that's interesting. And yeah, okay, so the given is that they have the same length, and yeah, okay, so this is just defining what they look like. So let's look at some examples. Like I don't really have an idea on how to do this straight away, but let's see. So so we have nums1 looks something like this. Nums2 looks something like this. So there are four triplets such that like there are four triplets that works for this. So that would be wait, actually, is there any order for the triplets, or is it just okay? So it is a set, so it doesn't really matter like the order, I think, right? Yeah, does it say that x is like does it say that x has to be smaller than y? It has to be smaller than z? I don't think so. Yeah, I don't think so. Yeah, so you can have something like this, right? So like you have this, which is wait, the four good triplets are okay. Wait a second. So it is saying that 403 is a good triplet, but then 4 represents 2, 0 represents 4, and doesn't 3 represents the 3 here. So it will be 2 is smaller than 4, which is not smaller than 3 though. So I'm not sure what is happening here. I have to read the question again. So a set of three distinct values, which are present in increasing order by position. By position, increasing order by position. Wait, so if we consider pos 1 phi as the index, Yes, the index of value phi in nums1. Uh, maybe I'll look at example 1 first, so we can kind of have an idea. Yeah, so 201. Huh? Wait, what? Wait, I'm probably like misunderstanding the question. So pos 1 phi is the index of the value phi. Oh, okay, so it's actually like the other way around. So what does that mean? So if x is 2, right, because the position is here and then 0, the position with the position for 0 is 1, and then the position for 1 is 3. So I think like you have to actually look at the elements to find out yeah, this question is kind of confusing, not gonna lie. So yeah, why does 213 work? I think it works because like it is in that order. And if we look here, right, so I think it is like so you have these order stuff, right? But then yeah, so you want to find triplets. So like let's say 213, right? Wait, 213 doesn't work. Yeah, wait, so if you look at like 013, we can see that like in nums2, 013 also goes in the same order. So therefore therefore it works. So actually I think like if we have something like this here, we want to map these numbers so that nums2 becomes like 0, 1, 2, 3, 4. But yeah, the question is like how do we map it? Because like if it is 0, 1, 2, 3, 4, so like because this is 0, 1, 2, 3, right? We can really just look at nums1 and we'll be able to find like how many how many increasing like we can kind of use like DP to find out how many triplets are increasing. So like for example like 013, and if we can map it like this, we know that it is going to wait, actually what do we know? Yeah, if we can map nums to like in this order, we can just check nums1. Like we just find the number of triplets that have like the first element as the smallest, and then second largest, and the third being the largest. Yeah, so actually let's look at example 2 and see how we can actually do this mapping. Right. Yeah, so something like 413 works here because it works here. Yeah, how do we actually want to map it though? That's the real question. Well, the other thing is we don't map, and like we kind of just keep track of. So like for example for 4, like obviously like if there are no constraints on nums2, we can just look at 4 and then like we can just find like for all the stuff afterwards, like how many more options do we have. Well, if we are doing like the n squared way, it would be like looking at each like 2 pairs, and then like I can find the, like basically you can just find out. Yeah, but I think the mapping thing could be good though. Um, how do you want to do this? Yeah, this question, the permutation and the position thing is like really confusing me. Um, Maybe you can try draw some stuff out, see what we can see. So 0, 4, 1, 3, 2. We want to, and we have like 4, 1, 0, 2, 3 here. So if we map, yeah, actually what happens if we just map like the 4 to 0, so we want to do this map, but that means we also have to change these numbers, right? So 0, so 0 goes to 2, 1 goes back to 1, 3 goes to 4, and then 2 goes to 3. So now we want to find, yeah, actually, do we want to do this mapping, or like, so you have like this is like the function, right? So you have this way, but then you can also do the inverse. But I need to like play around with it first to like really, I guess, find out what we can do. But actually, I think mapping it this way kind of makes sense, because like if you look at the good triplets, well, all of them start with a 4, right? Because 4 is at the beginning, which makes sense because like we have a 0 at the beginning, so obviously like it will be a lot easier to use that 0 because it is more than all the other numbers. Yeah, so we'll get like 0, 1, 3. What else do we get? We'll get 0, 2, 3. We'll get 0, 2, 4 and 0, 1, 4. Do we get any other stuff? I don't think so. Wait, but if we look at this, do we get like exactly what they have here? So 4, 1, 2, 4. So I'm looking at the positioning, right? So 4, 1, 3, it will be this one. 4, 0, 2, it will be this one. Yeah, actually, maybe that will work. So we want to map the permutation first using this, because like if you think about it, basically the second array defines like the new ordering of the number. So if we map it back to like our convention ordering of the number and mapping like nums1, we can kind of like just convert it and turn it into the like how many triplets that are like in increasing order. And well, if we are looking at like the how many triplets are in increasing order question, well, it would be yeah, we can just do like some DP stuff. So well, obviously the first one you wouldn't be able to actually, yeah, actually, like for DP, how do we want to define it? I think we want to define it such that the number we are looking at is the midpoint, I think. So we have to like know how many numbers are on one side, how many on the other side. Yeah, so at first, so we want to add all the numbers to the right side, right? Maybe I'll draw it down here, so left and right. Yeah, I'm just like trying to. I think I'm getting close, but I still need to like really think hard about this, to like really get the solution. So if we look at 0, we're gonna have like 1, 2, 3, 4 on the right. So I think like the number of triplets we can form would be the number of numbers that are smaller than our current number on the left, and the number of numbers that are bigger like on the right. So what does that remind us? Well, sorted list, right? Well, in C++ it will be like order set, but in Python we don't have that luxury, so we have to use sorted set. But sorted set allows you to um remove, and um it allows you to add remove elements in log n time, which is why it is like really good. And well, because we need an n log n algorithm, right? So yeah, but yeah, so let's keep looking for now. So 0, obviously it doesn't have any elements on its left, so we just look at the next thing. Well, so we see a 2, right? So that means we want to remove the 2 on the right, and then we want to add um the previous number that we have just seen. So we have 0 here. The other good thing about sorted list is I can just use bisect to quickly find how many elements are smaller than our current element. And well, the same thing for right, like for the right elements, right? So like if we bisect using 2, like we'll get 3 and 4. So that means we have one element here, 2 elements here. Well, that means we can form 1 times 2 amount of triplets if we have 2 as the midpoint. And then like we just do the same thing for 1. So here we're going to add 2 here, remove 1 there. And again, we will have 1 element here that works. And then we have 2 elements here, so it'll be another 1 times 2. And then when we do 4, we're going to remove 4 here, we'll add 1. But obviously 4 it doesn't have any stuff. It doesn't have any numbers that are greater on the right side, so we don't have anything. And for 3, there will be like nothing left here. So yeah, I think that's how you solve it. So let's just try to code it up. Yeah, I think we should code it up now. So first of all, we want to have a map. So map to convention order. Yeah, so we want to map the first number to 0, and then so like we want to map it to the index, right? So what we can do is I have a better idea. So we can have the actual number mapped to its index. So for index number in enumerate nums2, so that's going to turn our ordering back into the convention ordering that we know. So like 0, 1, 2, 3, 4. And then we want to map nums1. So we want to set nums1 into map convention order of the number for num in nums1. So actually, this will work. So like for example, like 4 will be mapped to 0. So like if it is a 4 here, like we'll get a 0 here. So we're gonna get the sorted thing. And then what we want to do is we have left and right. So both of them would be sorted list. So that also means we have to add from sorted containers import sorted list. For the right one, we want to add all the elements on the right, well, into we want to add all the elements except the first element into the set of right numbers, right? So and then what we can do is we can just do for I in range 1 all the way up to the length of nums1 minus 1, because if you think about it, if we have the first or last element as the midpoint, like as the middle number, we can never form any triplets, right? Because like like either of them have one side that's just completely missing. Yeah. So what we can do is we can add the previous element in first. So nums1, we can add I think, I minus 1, and then right, we want to remove we want to remove the current element that we're looking at, and nums. So after we have done this, we want to get the number of elements smaller than current midpoint on the left, and then we want to get the number of elements greater than current midpoint on the right. So for this, we can just use bisect, which I think it should be built in for sorted list. Yeah, so we can just do index. I guess like num left. So we can just do left dot bisect left. I think we can just do that. Nums1 I, and that's gonna give us the index that it should go in. If we are like adding that number, right? So the number of elements, so like if it is like index, like let's say index 1, then that means there are like only one element smaller than it on the left. So we'll just leave that as it is. For the number of right though, it should be right bisect left. So here we will have gotten again the number of numbers that are smaller on the left hand side, but then we actually want the right hand side. So we want to find out how many elements are in right. We want to get rid of, we actually want like all the numbers that are greater, right? So this gets all the numbers that are smaller, and we guarantee that there wouldn't be duplicates because we have like a permutation of this, so all the numbers are unique. So after we have done that, what we can do is so number of triplets. So we can just do number of triplets. Well, if we have like I elements on the left that are smaller, K element on the right that are bigger, we can form I times K amount of triplets. And then at the end, we can just return number of triplets. I'm not sure if add and remove is what you use here. Nums2. Yeah, the other thing I'm not sure is like if you do add and remove, I'm pretty sure these are log n, but we will see. If it works, that means okay, it worked, so that means it is log n. I actually looked into how sorted lists work. So in C++, if I'm not wrong, which I could be very wrong, they actually use a self-balancing tree for an order set. So for example, if you have like 1, 2, 3, 4, you have like let's say 2 as the root, and then you have like 1 here, you have 3 here, and 4 here. So basically like all the numbers that are smaller goes to the left, all the numbers that are greater goes to the right for every node. And let's say you want to add 5 in, right? Well, it will go here, right? But what self-balancing tree does is if there's a height if there's a height difference of 2 or more, it will rotate itself. So actually like you can rotate this into like into something like this, right? And like you can still see that the stuff that goes to the left is smaller, the stuff go to the right is bigger, and it's true here as well, right? So like it can rotate and like make sure that um well like make sure that it doesn't have like a really long linked list, which basically makes like the search ON sometimes. So like this will keep the time complexity log n. Uh, so that's how C++ does it. But when it comes to Python, they put the numbers into like blocks. So you have like 1, 2, and 3, 4. And let's say you want to add 5 in, like you put it here, right? But then like when you want to add 6, well, this block like could be too big. So there's like a set size of like how big the block could be. Uh, so because like 6 is too big, like it will create another block. And then like when you have too many blocks, um, so like let's say you have like 7, 8 as well, right? Uh, you have to think about it as like a block of blocks. But now it has too many blocks, so it is going to like split itself into like two different blocks. So right now, like when they are searching for, let's say 6, well, they know that this block contains like 5 to 8, right? So it's going to look here, and then like they will look at these blocks, and like you can see that. So like basically, it's by this splitting kind of process that that they achieve like a log n add remove bisect kind of time complexity. So yeah, actually like sorted list is very, very interesting. Unfortunately, um like some most of the like competitive programming stuff, they don't actually allow this because it is a third party library, I think, so it's not built in. But yeah, this question is quite interesting. It is quite confusing at first sight because like you're not too sure what they actually want here. But I think like after you like understand and then like especially like they give you this example, which is kind of a dead giveaway if you ask me. Like for the mapping trick, but yeah, I guess like this part here, like the triplet part after sorting quite um is quite a well-known problem. I'm not sure though, but yeah, thank you for watching. If you got up to this point, um thank you, I guess, because I don't think I would have the attention span to watch a video for that long. But yeah, thank you for watching, and I'll see you tomorrow.